continue our discussion on the solutions of the linear harmonic oscillator problem. In my last lecture, I had shown that the most general solution of the one dimensional Schrodinger equation is given by C n psi n of x e to the power of minus I n plus half omega t, where n goes from 0 to infinity. Then we said that let us assume that at time t equal to 0, the wave function of the oscillator associated with the oscillator is given by e to the power of minus half xi minus xi 0 whole square. Such a state is known as a coherent state of the oscillator, coherent state of the oscillator. Now, then we can find out the corresponding to psi of this form of the wave function at t equal to 0. I can find out C of n, and that will be psi n star of x and multiplied by psi of x comma 0 dx. All limits are from minus infinity to plus infinity. If I carry out this integration, as I mentioned last time, one can get an analytical expression 1 over n factorial half xi naught square, half xi naught square raised to the power of n by 2 e to the power of minus half xi square. Sorry, 1/4. So, therefore, mod C n square will be equal to 1 over n factorial half xi naught square raised to the power of n e to the power of minus half xi naught square. You can now see that if I sum mod C n square over n, then let us suppose this I denote by alpha. So, this factor I take outside. So, e to the power of minus half xi naught square. So, this will be alpha to the power of n divided by n factorial, where alpha is equal to half xi 0 square. So, this is just e to the power of alpha or e to the power of half xi naught square. So, that will cancel out with this and you will get 1. So, mod psi n C n square represents the probability of finding this system, the oscillator, in the nth state. Now, I have an expression. So, this is the normalization condition that n is equal to 0, 1, 2, 3 to infinity. This is equal to 1, and that is what should be expected, because the wave function initially at t equal to 0 is normalized. So, therefore, I asked myself that what will be the value of energy that I will get. The answer is that you can get any of the energies, and there is a probability C n square for obtaining the nth eigen energy. So, as we know, the possible energy levels are E is equal to E n is equal to n plus half h cross omega. So, the expectation value of E that you will get will be the expectation value of n plus half within brackets multiplied by h cross omega. And what is the expectation value of n? this will be summation n mod C n square, and I have just now written the value of mod C n square. So, if you see this, that mod C n square is given by this. So, if you sum this up, then it will be n by n factorial. So, that is n minus 1 factorial. So, now n will go from 1 to infinity, and this is alpha to the power of n, alpha to the power of n, and e to the power of minus half xi naught square I can take outside. So, this is e to the power of alpha. So, I take alpha outside. So, e to the power of minus alpha outside and alpha outside, and so this will be alpha to the power of n minus 1 by n minus 1 factorial. So, this is n equal to 1, 2, 3, where alpha is equal to half xi naught square. So, this is e to the power of alpha. So, therefore, this will come out to be alpha, which is equal to half xi naught square. So, this is the value, average value of n that you will get. Similarly, you can write down what is the expectation value of n square. I leave that as an exercise, and the final result will be that the spread in the, so the expectation value of n will be equal to half xi naught square. Similarly, you can calculate what is n square, and then let us suppose the spread in the value of n, that is delta n is equal to this. I leave it as an exercise for you to calculate the expectation value of n square, and you will find that this will be square root of n, that is xi 0 divided by under root of 2. Now, let me give you let me do some numerical examples. So, you will have, let us suppose that xi naught, you will remember that xi is equal to gamma x, and so therefore, xi naught is equal to gamma of x naught. Now, gamma, if you remember, that was equal to under root of mu omega by h cross. Now, let me take a very simple example, that mu is equal to, let us suppose, 2 grams. I am using CGS system of units. Omega is equal to 1 second inverse, and h cross is approximately 10 to the power of minus 27, it is 1 point something erg second. So, if you substitute it here, so I consider a classical oscillator, the mass is 2 grams, omega is the time, the 2 pi by t is about 1. So, the time period is of the order of 1 second, and h cross is of course the Planck's constant divided by 2 pi is 10 to the power of minus 27 erg second. So, if I calculate this, so this will be 2 into 1 divided by 10 to the power of minus 27. So, this will be 2 into 10 to the power of 27. So, under root of 20 into 10 to the power of 26. So, this is about 4.5 under root of 20 into 10 to the power of 13 meter inverse, centimeter inverse, sorry. So, you see the value of xi naught, is very large. So, if the amplitude of my displacement of the oscillator is say 1 centimeter, so xi naught is equal to gamma times x naught. So, x psi naught will be gamma is 4.5 into 10 to the power of 13 into x naught, let us suppose it is 1 centimeter. So, I have a particle of mass 2 grams having a time period of the order of 1 second and the amplitude is 1 centimeter. So, the value of psi naught is very large. So, this is equal to, so therefore, the value of expectation value of n, please see this, the average value of n will be half psi naught square, 4.5 square was actually 20. So, 20 into 10 to the power of 26. So, this is about 10 to the power of 27. So, the states which have the quantum number of the order of 10 to the power of 27 gets excited, and this is expected, because you see E is equal to n plus half h cross omega, and the total energy of the classical oscillator, as you know, is half mu omega square x square, sorry, x naught square, which is the amplitude. So, mu is 2 grams. So, half into 2, omega is 1 and x naught is 1. So, this is 1 erg. H cross is 20 to the power minus 27. So, n must be 10 to the power of 27, this is what we get. So, therefore, we are exciting states with very large quantum number. This is actually what I am discussing is Bohr's correspondence principle, that in the limit of classical mechanics we have extremely large quantum numbers. And then how many states? The delta n, the number of states which are approximately getting excited around 10 to the power of 27 is square root of that. So, this is of the order of, the square root of that will be 3 into 10 to the power of 13. So, this is 30,000 billion states, or 30 trillion states. So, I hope I am able to make you understand that you have, this is the ground state of the oscillator, and this is n equal to 1, n equal to 2, n equal to 3, and you come here and it is n equal to 10 to the power of 27. So, there are so many billions and billions and billions of states are there. Here a very large number of states get excited. This is the delta n. Delta n is very large. Delta n is of the order of 3 into 10 to the power of 13. So, this is about, this is equal to actually 30 into 10 to the power of 12, that is 30,000 billion states, 30 trillion states. But the spread of energy is very small, because this is only 10 to the power of minus 13 of 10 to the power of 27. So, as n goes from 10 to the power of 27 to n to the power of 27 plus 3 into 10 to the power of 13, the change in energy is extremely small, because here E I know was 1 erg, and this will be 1 erg plus 1 plus how much? If I take an n value of 3 into 10 to the power of 13 into h cross omega. H cross is 10 to the power of minus 27, omega is 1. So, this is 3 into 10 to the power of minus 14. So, we are adding 1 to a number which is extremely small in comparison to 1. So, therefore, the energy of the classical oscillator is very precisely defined. Delta E is very small, delta X is very small, delta P is very small, and that is the domain of classical mechanics. In the domain of large quantum numbers, we have classical mechanics. We had in the just before we finished our last lecture, we had said that x was equal to x naught cos omega t, and similarly we had found out x naught square, x square is equal to something. So, the delta x we had found to be equal to 1 over square root of 2 gamma. Now, what was gamma equal to? So, this was mu omega by h cross. So, this will be h cross by 2 mu omega. Similarly, one can calculate delta p also. So, what was x equal to? X was equal to integral x mod psi square dx from minus infinity to plus infinity, and that is a very straightforward integration to calculate. So, let me calculate delta x. I am assuming the amplitude to be 1 centimeter. A 2 gram mass having a time period omega is equal to 1 second inverse. So, the time period is 2 pi by omega. So, about 6 seconds is the time period, and the amplitude is 1 centimeter. So, my uncertainty in x is 10 to the power of minus 27 divided by 2 into half into 1, 2 into 2, mu is 2 grams. So, this will be 4, let us suppose I take 10 outside, 10 into 10 to the power of minus 28, and this is 4. So, my delta x comes out to be, please see this carefully. So, this comes out to be 2.5 into 10 to the power of minus 28 centimeters. So, 2.5 is about say 1.6 into 10 to the power of minus 14 centimeter. So, this is the uncertainty in x. Similarly, one can calculate the uncertainty in p. So, that comes out to be under root of mu omega h cross by 2. Mu is 2 grams, so 2 cancel out, omega is 1, h cross is 10 to the power of minus 27. So, this is 10 into 10 to the power of minus 28. So, this is about 3 into 10 to the power of minus 14. The unit of momentum will be gram centimeter per second. And if you multiply this out, so this will come out to be delta x, delta p is about 5, that is half into 10 to the power of minus 27. So, this is equal to half h cross. It is a very important result that I have derived, that for my classical oscillator, delta x, delta p is of the order of half h cross. So, is my uncertainty principle applicable to the classical oscillator that I see in my first year lab? The answer is of course yes, but both position and momentum are determined with a tremendous degree of accuracy, and that is a consequence of the fact that the value of h cross is extremely small. So, once again, when I have a pendulum and I make it vibrate, make it oscillate like this, then I ask myself, to what state of the oscillator does it belong to? The answer is it does not belong to a particular state, it belongs to a superposition of states. Then you tell me what states are being superposed, and the answer is we are superposing states for which the quantum number is 10 to the power of 27 about, and in that quantum number the spread in n is 10 to the power of 13, 3 into 10 to the power of 13. So, for n equal to 10 to the power of 27 plus minus 10 to the power of 13. So, that is the number of states we are exciting 100 trillion states around n equal to 10 to the power of 27. So, although we are exciting a tremendously large number of states, but because H cross omega is an extremely small quantity, so therefore, the energy is also very precisely defined. And delta E by the spread in the energy divided by the expectation value of energy is extremely small, 10 to the power of minus 13 or so. So, that is my classical oscillator. So, therefore, I will again go back to the slide that I had shown, because that is very important. So, this is my coherent state, and let me evolve. So, it is a packet, it is a wave packet obtained by superposition of 1,000 trillion states. So, here I have taken only a xi0 value which is about 1000 or something like that, but we have just now found that the value of xi0 is extremely large. So, this packet will become extremely small in width, and this is how the packet will evolve with time. So, I hope by now you know the relationship of the classical oscillator to the quantum oscillator. In quantum mechanics, the energy levels are quantized, but the classical oscillator that we see in our first year lab, it corresponds to n equal to 10 to the power of 27, and the spread in the n value is also large, but it is extremely small in comparison to the value of n, and so therefore, you will have almost the energy is very precisely defined. So, let me mention one more thing, that we had discussed this, but this is the value of Cn that we obtained. If, for example, the expectation value of n is 10, then these are this is the on the vertical axis you have Cn square, and the horizontal axis it is n. So, the probability is maximum for around n equal to 10. So, these are the number of states that get excited, about 10, 12 of them, when average value of n is 10. For a classical oscillator, average value of n is 10 to the power of 27. So, when n average value of n becomes 100, then it occupies about 100 states around n equal to 100. So, average the spread in n is about 10. When n becomes 1 million, then around 1 million so many states are getting occupied. The number of states are large, but the energy spread is extremely small. So, we finish this here. Now, we will go back to the solution of the Schrodinger equation. However, before we start solving the Schrodinger equation, I would like to solve a differential equation which is known as the confluent hypergeometric equation, and the solution of which is not only important, for the harmonic oscillator problem, but also for the hydrogen atom problem, for the three-dimensional oscillator problem, and many other problems. So, once if you understand how to obtain the solution of the confluent hypergeometric equation, then it is possible, it will be very easy for you to understand how to obtain the eigenvalues corresponding to many problems of interest in quantum mechanics. So, we try to solve the equation x d2y by dx square plus c minus x dy by dx minus a y of x is equal to 0. This equation, where a and c are numbers, this is known as the confluent hypergeometric equation. Actually, the name is quite big, but the solutions are very easy to understand. So, I would just like you to patiently work out the solutions using the series solution method, and once you understand that solution, the solution corresponding to the hydrogen atom problem and the harmonic oscillator problem and the three-dimensional oscillator problem will become very, very easy. So, we will use the power series method, which most of you may have already studied. This is also known as the Frobenius method. And the method involves that I make a power series expansion of y of x in powers of x. So, the constants are, usually it is written as C of r, but since the constant c is appearing here, so we will replace this by dr x to the power of p plus r, where r goes from 0 to infinity. This is known, this is the fundamental equation which is used in the power series expansion. So, I differentiate this once and I differentiate this again. So, y prime of x, which is equal to dy by dx, the summations are all from 0 to infinity. So, this will be d's of r p plus r, I will do it carefully, p plus r minus 1, and d2y by dx square will be equal to summation r dr, as all of you will know, p plus r, then I have to differentiate this. So, I will get p plus r minus 1 x to the power of p plus r minus 2. The next step is I substitute this here, I substitute this here and write down the equation. So, if I multiply by x, so I will get summation d's of r p plus r minus 1 x to the power of p plus r minus 1, because I have multiplied by x. So, it becomes like this, plus c times this equation plus c times dy by dx. So, c times dy by dx, that is dr, one just has to do it patiently. I will do it once, p plus r minus 1 minus x times this. So, x times this, that is summation dr p plus r and x to the power of p plus r minus a y of x, that is minus a summation dr x to the power of p plus r equal to 0. What I do next is I multiply the whole equation by x to the power of 1 minus p. The summation is over r, summation is over r. So, I multiply the whole equation by x to the power of 1 minus p. So, if I do that, what I will obtain is the following: summation d's of r, I will have to write down this again, p plus r minus 1, and the multiplication is 1 minus p. So, this is x to the power of r plus c dr p plus r x to the power of 1 minus p, that is x to the power of r minus, or if I take these two expression on the right hand side. So, I will get is equal to dr p plus r plus a, p plus r plus a times x to the power of r plus 1, r going from 0 to infinity, all of r's are going from 0 to infinity. So, just write these down. So, on the left hand side, so let me combine these two. So, you will have summation, please see this, d's of r, p plus r I can take common, p plus r minus 1 plus c, p plus r minus 1 plus c x to the power of r going from 0 to infinity, and here it will be r equal to 0 to infinity dr p plus r plus a x to the power of r plus 1. On the left hand side there is an infinite series, on the right hand side there is an infinite series. Now, if this has to be valid for all values of x, then the coefficient, all the coefficients must be equal. Now, let me illustrate this. I am sure most of you know this, but let me illustrate this, that if I have an equation like this, say a x plus b is equal to 0, then this equation is satisfied only at x is equal to minus b by a. For this equation to be satisfied for all values of x, you must have a is equal to 0 and b is equal to 0. Then and then only this equation will be valid for all values of x. Let me give you another example. I have a quadratic equation, a x square plus b x plus c equal to 0. Now, for given values of a, b and c, as you know, the roots of the quadratic equation, you know, minus b plus minus, so on and so forth. This is satisfied for two values of x. However, if this equation is to be valid for all values of x, then A must be 0, B must be 0 and C must be 0. This is an identity. This has to be valid for all values of x. And so, therefore, on the left hand side, let us suppose I have a plus b x plus c x square plus d x cubed and so on, and on the right hand side you have alpha plus beta x plus gamma x square and so on. Then for this to be valid, this equation to be valid for all values of x, A must be equal to alpha, B must be equal to beta and C must be equal to gamma and so on. So, that is the property of an identity. So, you have here an equation. So, the first coefficient is d0. So, d0 r is 0. So, p multiplied by p minus 1 plus c, x to the power of 0. So, let me cut it out, So, I have d0 p into p minus 1 plus c x to the power of 0, which is 1, plus d1 p plus 1, r is 1, p plus c x plus something like x square plus x cubed, and on the right hand side this is d0 p plus a x plus d1 p plus 1 plus a into x square and so on. So, the coefficient of this should be equal to this should be equal to this, and since there is no x to the power of 0 here, this should be 0. But d0 cannot be 0. So, you must have p into p minus 1 plus c must be 0. This is known as the indicial equation. And therefore, we must have the roots of the indicial equation are p is equal to 0 or 1 minus c. So, these are the roots of the indicial equation. Then you will have from this equation, if you write this down, I can rewrite this in the following manner. So, please see this, I am rewriting this equation and I will obtain from dr p plus r minus 1 plus c x to the power of r. This is equal to, from r equal to 1 to infinity, dr minus 1 p plus r minus 1 plus a x to the power of r. So, now I have equated that, and so therefore, dr by dr minus 1 will be equal to p plus r minus 1 plus a divided by p plus r into p plus r. Most of you may have done this before. So, I take this dr minus 1 here. So, this is known as the recurrence relation. And initially I had written down that the roots of the indicial equations are p can be either 0 or 1 minus c. Let me take the first value p equal to 0. So, we will have dr is equal to p equal to 0. So, therefore, this will be r minus 1 plus a divided by r into r minus 1 plus c dr minus 1. So, you will have, please see this, when you put r equal to 1, so you will have d1 r equal to 1. So, 1 minus 1 is 0. So, a r is 1. So, 1 times r is 1. So, this is 0 times c into d0. d2, so r is 2. So, 2 minus 1 is 1. So, this is a plus 1 divided by 2 into r is 2, 2 minus 1 is plus 1. So, c plus 1 d1, and d1 is a into 1 into c into d0. So, this comes out to be, if I put a here, a into a plus 1 divided by c into c plus 1 into 1 over 2 factorial, 1 into 2 into d0. Let me write down one more term, and that will be something like this. So, I found out d1. So, let me write down one more term d3. So, r is 3. So, 3 minus 1 is 2. So, this is a plus 2 divided by 3, and 3 minus 1 is 2. So, 2 plus c into d2. So, into d2, and d2 is given by this. So, you will get a into a plus 1 into a plus 2 divided by c into c plus 1 into c plus 2, and then it is multiplied 2 factorial multiplied by 3 is 3 factorial into d0. So, you obtain the infinite series, that is like this. F, you write this down as f11 a c x. This is one of the solutions, which I had written down that as dr x to the power of p plus r. P is 0. I have assumed p equal to 0. So, this will become dr x to the power of r. So, you will have, if I take d0 x to the power of 0 plus d1 x plus d2 x square and so on. So, if I assume d0 outside, so I get 1 plus x d1 by d0. So, that is a by c x by 1 factorial plus a into a plus 1 into c by c plus 1 x by 2 factorial plus a into a plus 1 into a plus 2 into c plus 1 into x square, and this becomes x cube by factorial 3. This infinite series, when d0 I assume to be equal to 1, is known as the confluent hypergeometric series. So, I have one of the solutions of the differential equation is y is equal to f11, that is y1 of x. y1 of x is f11 a c x This is known as the confluent hypergeometric function. This is an extremely important function and it is very easy to remember. So, f11 a comma c comma x is equal to 1 plus a comma c x factorial 1 plus a into a plus 1 by c into c plus 1 x square by factorial 2 plus a into a plus 1 into a plus 2 c into c plus 1 into c plus 2 x cube by factorial 3 plus this is an infinite series. Obviously, c cannot be 0 or a negative integer, c cannot be a 0 or a negative integer, the function will blow up. This is one solution and the other solution, as you can see, is p was equal to 1 minus c and the other solution will be x to the power of 1 minus c. I leave that as an exercise, f11 a minus c plus 1 2 minus c comma x. And if actually if c is a positive integer, say let us suppose c is equal to 3, then this becomes negative. So, that will blow up. So, the general solution of the differential equation is given by the following. So, we started out with the equation x d2y by dx square plus c minus x dy by dx plus minus a y of x. For this you must remember, for c not equal to 0, plus minus 1, plus minus 2, plus minus 3, the general solution of this equation is c1 f11 a c x plus c2 x to the power of 1 minus c f11. There is a superscript, there is a subscript on both on the left as well as on the right of f. So, this will be f11 a minus c plus 1 into comma 2 minus c into x. What we will do in our next lecture is that you remember that we had the equation like this, d2 psi by d xi square. The Schrodinger equation was given by lambda minus xi square. We will transform this equation into an equation which is hypergeometric equation, and we will find that the values are c is equal to half, small c becomes equal to half. We will transform this equation into a differential equation of this type and we will obtain the solutions for the linear harmonic oscillator problem. So, with this we end today's lecture, and we will request that you go through the solution of the confluent hypergeometric equation, and that is given in any book on mathematical physics, and go through that before you come to the, in any case the analysis that I have given is complete by itself, and next time I will talk on the behavior of the series for large values of x, and we will obtain the solutions of the harmonic oscillator problem. Thank you.